Let's start. Who am I? My name is Paul Heimann. I'm a data engineer here at Xing at the data science team, and we are mainly responsible for recommendations and search. For myself, I build services around our ontology and a subset of our recommenders. So when you have problems with your recommendations or you get strange recommendations, I would say it's usually your fault because you use Xing the wrong way. Can't do anything about that. I also have a public GitHub account. Usually I look something like that. That's my image and that's my handle. So if you want to have the slide, you just have to go to github/pheyman, and then I pinned this project for this talk there, so it should be on the front page. Yeah, okay. That should be for the organizational stuff. So then let's start with our talk. Name is the Functions and Monads into the Rabbit Hole. What is this talk about? We will speak about the basic ideas behind functional programming. What is the fundament of functional programming? So that all of you have a basic idea of it. What is the idea behind it? We will speak about first concepts, including functors and monads. And hopefully I will provide you with some good code examples. We'll see about that. What this talk is not about. I don't try to pull you into search of functional programming. And I know those who don't try to add to this flame war between functional programming and object-oriented programming, functional programming and imperative programming, functional programming and every other programming paradigm you can find on this planet. Because in the end, it's just an architectural decision you make about how you write your code. It doesn't matter if you use one or the other paradigm. It's completely opinion-based decision you do there because based on what you prefer, and you can write good or bad code with either or with all paradigms. Doesn't make a difference. Just functional programming is the one paradigm I prefer, I actually like. If you want to discuss with me about what is better about OOP against functional programming, then we can do this afterwards in a private talk. Then I can show you that you are wrong. Yeah, I show you the door. There you can go then outside. Okay, that's with that. What is functional programming? What are the basic pillars behind or of functional programming? Separation of operation and data. It's as simple as the title says. So you have data in the form of primitives like double, integer, float, you name it, or in the form of complex structures like case classes where you put different or multiple primitives into one structure. This or data don't have behavior, so this data don't do anything. They describe some data or information, but they can't do anything about it. On the other hand, you have operations. They are the complete opposite of data, so they only provide behavior. You can put in information, you can transform this information, get out new information, but they itself don't store information or data or or keep it kind of a state. So you have a clear distinction between data and operations. You have a clear distinction between two different concerns. So you can handle these two concerns separately. This data are immutable. What does that mean? It never changed. In the moment you create data, they stay the same for their whole existence. If you want to change or if you want to create new data, as I already said, you have to create new data. So if you want to create a new score of the type double, you have to take the old one and do some operations on it to create a new one. The old reference or the old data stays the same. The same example works for the case class where you have to create a new one when you want, for example, in this case, increase the age of the user. this also has to be reflected by these data structures. This list implementation, I would say, is one of the easiest. You just have an element of some type and the rest of the list. Once you create this list instance or this list structure, you can't change it anymore. The only thing you can do is you have to create a new one when you want to add a new element or remove one or want to update one. What's the advantage of that? When you have a reference on some data or information, you can be sure that it's always the same. Nobody can change it. You have always a guarantee that you work on the same data at every point in time. On the other side, you also know if you want to change something that you don't influence other parts of the code. This, again, a separation of concerns. So I know I can work with my data I get without interrupting or changing behavior in other parts of the code. And at the same time, I know that my data is stable. So now we talked about the data side. Let's go to the operations side. And our operations are, as the name says, functions, and in the sense of mathematical functions. So I have, or what is a mathematical function? It's a mapping from an input to an output. And this input always maps to the same output. It doesn't depend on the time, on the environment. The same function always creates the same output for the same input. And furthermore, functions don't have side effects. So we also, well, in this case, we call it the pure function. As you can see in the first example, when I put in a user A with the age of 26, I always get back a user with the age of 27. Doesn't matter if I do it today, tomorrow, or 1 year, right now at this spot, or in the next room, doesn't make a difference. On the other side, you have unpure functions or functions methods which share side effects. One example would be you use some random generator. So I can call this guess score functions 20 times and get 20 different results. The second example would be something which has side effects. This example would be the load user function or method. Maybe I get a user at a certain point in time. Maybe it fails because you have a timeout or the server is not available or you have a network partitioning. So this is not, as the function is described, you don't have the guarantee that you get for a certain input always the same output because it can break. It is context sensitive. The next thing about functional programming is composability. What does that mean? I can stick together different functions. Easy as that. I mean, you write small or simple functions which do exactly one thing. The Unix principle, they do one thing and they do it good. You can test them. You know what they do. You stick them together and create more complex functions. And in the end, in this way, you create whole programs. So you build up or you solve small problems, stick them together to solve an even bigger problem, stick them together to solve an even bigger problem and end up with your program. That's what we want to do in functional programming. And the last part is about side effect abstraction. Because we have one problem, we have to interact with the real world. Otherwise, your program doesn't make any sense at all. So we have to write to the console or ask some other service or have to query data from a database. But within our logic code, we don't want to have the side effects. We want to have our pure functions, our pure code. So we have to abstract about the side effects. We have to just describe them rather than actually execute them. As you can, or in this example, you have the load user age function. In this upper example, it actually calls a database or some REST servers and loads the user. So you have the side effect. Or you do it the second way, which would be the function way. You just describe what you want. You say you get some context F, in this case a functor. We will talk about what a functor is later. Just take it as it is. And we have some loader there that just says, okay, this loader loads the user when he gets a user ID. I don't know how he does it, and I don't care. I just describe what I want. So at this point, I don't have any side effects in my code description or code at this point. And that's, at least as far as I understand, all about when you read the stuff about if you use functional programming, you can reason about your code, whatever that means. For me, it says, I understand what this code does. I look at this code, I know, okay, I have a functor, I know it does this, that, and that. And I have this loader, which returns a functor with some user in it. So I can reason about it. I understand what this code does. I don't have to know some library or what protocol is used because it doesn't matter. I just describe what I want. Okay. At least for me, these are the basic pillars of functional programming. Are there first questions? If not, then I just continue. No, okay. How does it work? Of course, you have to use functions. That's the basic idea behind functional programming. We talked about it, but that's not the... yes, there's... You can have a own talk about how you use functions, Scala, and stuff like that, but in the context of just functional programming, there's not much more about it. The other big part of how functional programming works are type classes. Who knows what a type class is? Okay. Who used the type class? Or has used the type class? A bit less, I would say. So it's good that we repeat this stuff. Or introduce it, depending on the person. What does Wikipedia say? In computer science, a type class is a type system construct that supports ad hoc polymorphism. This is achieved by adding constraints to type variables and parametrically polymorphic types. Hard to read. Such a constraint typically involves a type class T and a type variable A and means that it can only be instantiated to a type whose member supports the overloaded operations associated with T. Exactly. I didn't get this description at all when I first read it. Not a bit. Took some time and tutorials and example code, and at the end, when you know what it is, then you understand the sentence. At least that was for me the way. So we also tried with an example. Imagine you have a behavior or operation you want to use for different types. In this case, we want to order something. We want to compare elements of the same type and want to get some ordering. How we do that? We create a trait depending on some type parameter, in this case A, and put in the description of the operation we need. So compare. We put in two elements of the same type and get back some integer. And one, or with the codes 1 for L is bigger, Z is -1 for R is bigger, and 0 if they're equal. We also could encode it with some other stuff to make it more type safe, but it's not relevant for this presentation right now. And this is more or less all what a type class is, at least in Scala. You have a trait describing some behavior, and this behavior depends on a type parameter. So in this way, you can control which types provide this behavior, because you have to provide an implementation for a type so that he can provide this behavior. How do we want to use it? Either we say, okay, we call order, provide, say, we want to order a user and call this function, or we build it into our own functions and just say implicitly there have to be some order for user. If there is no implementation, the compiler will tell you. So this will break during compile time and not during runtime. So you are safe at this point. Now we have two implementations just for the example. First for integer or for int. I just lazily reused the Scala implementation here and just wrapped it there. And again for users, and we say we want to order users by age. So if a user is older, then he is ranked up. And in the end, we just have to add some implicit resolution here to get the code a bit nicer. So we just apply this, or we just implement this apply function there. So we can write this lower or this line here to say I have an order for a user, and then I want to call this function. For your site, I talked about this line. So what does it mean for us? Why do we actually need this for functional programming? First of all, it's a nice way to give it type-specific behavior without intermingling data and operations. So you have your integer, but as said, it's just data, so it can't do anything. But you want to say, I want that integers can be added, which is behavior. So then you use a type class you call add, or be more creative about it. Add some function there which adds to integers, or which adds to elements, provide an implementation for integer, and you're good. So now you added, in this sense, behavior to certain types or to data. And the good thing is, and that's the point about polymorphism, we get this behavior for different types. So we can use this description, or we can use this type class just to say, I need this behavior, but I don't care which kind of type it is. I just need this behavior. So I make my code this way more generic, so I can reuse code which I usually have to implement again for different types. This was my kind of really small introduction to type classes. Again, I think you can have an own talk about this topic, but it should be enough for this talk. Again, some questions here? No. Good. So we had a bit of blah right now. I think it's time for a bit of code. So what do we want to do? We want to build a REST service. And I want to put a user into the REST service and get the most similar users back. So in the end, a recommender for friends or members, or don't know how you want to call it. This recommendation should be ordered by some score, because usually I want to have the most similar user at the top. I don't care about the worst similar user, because that's not the point of this task. Or if I want members who are or I can connect with, then usually I want to have this one which are kind of similar to me. And for this example, we want to read this user information from some I/O source. Otherwise, it's not really real world, because nobody has all this information in memory and just use it from memory. So that's our task. How does our data look like? First of all, we have a user. We just have an ID, a first name, last name, an age, a city, and a job. And you have a recommendation, or in short, just reco. A recommendation consists of a user and some score. Can be a double, an int, or something else. Doesn't matter at this point. And we also want to order recommendations, so we have to provide some implementation of our order type class. In this case, we say we order recommendations by the score. So we want the biggest score on the top position. That's the way we want to order it, or that's why we need this implementation. Then we need a way to score our recommendations, or to score our users, to say these two users are really similar or not. Therefore, in this case, I provided this interface where you just can put in a base user and some other user or some other element and get back a score, how good they both together, and provide an implementation for a user compared to a user. You just can add some fancy logic there where the question marks are. I don't really care how you compare them. Then we have our recommender function. Here we get a user, and again, because I'm lazy, you get all the other users you have in the database except the base user. So we load all the users. What we do is we take every single user from this list, we create the recommendations, use our scorer, create a score, how similar these two users are, Then we filter out all the users which have a score of 0, so they are completely, or in this case, they are completely dissimilar or unsimilar. I don't know how to tell us. And then we sort it by the score, so that we get the highest or the most similar user at the top. So what do we got so far? So far with our code, we have separation of behavior and data. So there's a check for that. We have immutable data. There's final case classes. You can't change it. This final fee, or was it like you can? I don't know. It's values. You can't change them. Maybe you can use reflection or something like this. Then yes, but that's dirty. And you have a pure function, or you have pure functions. So no side effect at all. That's nice and shiny, but what about the I/O stuff? I mean, we still have to get the user or find the user we add or supply to the service. We still have to fetch all the other users, and this is not functional anymore. We have to call some database or some REST service or some file, and usually you do this asynchronously because you don't want to wait for all the stuff. So it's a future, and it's something from the external world. And when we try to stick all this together, this doesn't really work, because you call this functions, or, well, let's call it operations because there are no functions or methods. You call this operations, and you get back a future of a user. Then we try to stick it into our create records function. That doesn't work because it expects the user, not some user in some side effect context. Next thing is you try to fetch all the other users. Still the same problem. This function or this operation wants a user, not a future of a user. And it returns a future of something, which again doesn't work. So we can't compose it. And we didn't hide the side effects. They're just there. They're actually in our code, in our logic code. So we have to do something about it. And every time you have to do something about higher kinds, or you want to do something with higher kinds, you start ending up with something like that. In this case, a functor. What is a functor? It's just a type class or a trait providing a function map. What does map does? Exactly does what you already know. You put in some f of a, for example, in this case, the function of the sequence of users, or the function of the future of a user, sorry. And you provide some function there, how you map from a user to something else, or a sequence of users to something else. What you get back is, again, a future of something. So you have a mapping of the types within some context f. This is already good, so we can use our fetch users accept function or operation, map over it, and apply it to our create records function. So we have composition there, but we still have the problem. Or what do you do when your function f, which you see in the signature of f of map, doesn't return a b, but again some f of b? Because what you end up is f of b, or a future of something, which doesn't make sense, and you can't work with that. So you need some functionality or behavior to reduce this. There we end up with the infamous monad everybody is crying about for some reason I don't get. What does monad provide? It's in the end an extension of a functor, and it just adds a pure function or operation which lifts up some value in your context. So let's say you have a user and you need the future of a user, then you say pure user and get back a future of a user. So it was lifted or is lifted into the context. And it provides a flat map. What it is, it's exactly what I needed or what I described before. I end up with something like a nested context and like a future of a user. And the flat map reduces that to a future back, or reduces that to a future. So it already sounds like this solves our problem we had with composition, because now we can supply the find user operation to the flat map, use the user we get back, supply it to the fetch user accept operation, get some future of a sequence of users back, and then we can work on that in the following code. If we apply it to our problem, this looks something like that. It's kind of nasty. You could also write it as a for comprehension, especially because Future already has this API or this code. But just for the effect of learning, I wrote it this way so that you see what is happening here. Okay, so we got our composition back. We can compose this stuff. We can build, we have 3 operations or functions there. We can compose them together and create a more complex one. But as I already said, it's the first 2 operations or side effect functions. We don't abstract about our side effects. That's the last pillar, the last point about function programming. We want to abstract about that. So we still have to solve this problem. And one way to solve it is to say, or it's in the end, it's the only way to solve it. You move the problem of side effect to the caller or the user of this function. You say it's not my problem, it is his problem. So you try to build an application where you have a really thin layer of side effects around your functional code. You try to make it as thin as possible. How do we do that? We have to, or when we want to do that, we have to somehow encode it in the return type. One way to do it is to say we don't return a value or data, not a value, but data, but we return a function again. And we say we have some interface there with two operations, in this case, find user and fetch users accept. And we don't say it returns a future, but we say it returns something abstract, something just a higher kind f. We don't, at this point, we don't care what f is. We just say it returns something in a context. But when we do this, how do you map over a function? Because now you don't have values or a future or option or whatsoever. You have a function. How do you map over a function? How does it work? How you put the function into a for comprehension to get back a function? The next slide maybe don't look that nice, but after a moment or a while, you get it, I hope. What we then need is called Kleisli. What is it? It's a monad for functions. It is just the way to provide map, flat map, and pure and all the stuff for functions rather than, or let's correct that, not for every function, but function which returns some context. It provides this interface so you can use functions in for comprehension so that you can compose this kind of functions. How does it work? Again, you have a map, but instead of value you get, before it was f of a or something like that, you have this function from a to f of b. And what you do is you call this function, get back the f of b, call a map on the f of b, and then you apply this f from b to c. Because that's the reason why we have this functor here in the signature and for your, because that is used so that you can execute the map on the f of b. In a way, you build a new function from a to f of c this way. You compose these 2 functions to a single new one, or a single new function. It works the same way for flat map, just the difference is that you again reduce the context from f of something to f of something. So, we have that. We apply it. Looks a bit noisy, but in the end, this is an example, so it's over-engineered anyway. It's the same as before, but instead of having or as this pseudocode I would call it, we have our function calls here. where we say, okay, I have my interface. I say I return this Kleisli or this function monad, which gets my interface user reader and returns a list of recommendations. So what I can do now is say, okay, I call one operation or a function from this interface. I call another one. I map over the results. And I use the results to create my recommendations. So, and I say, or at this moment, I say I need this f to be a monad. So I restrict this type to a certain description or to certain behavior, better said. At this moment, we have composability again, and we hide our side effects. This is just a description of what we want to do, but there's no indicator of how we're doing this, no indicator of side effects here. We can have an implementation of user reader which is completely side effect free. So when we execute this function, it's also still a function. We can have an implementation of user reader which uses a database or whatsoever, has side effects. Then the execution becomes also, or the execution of this function is also not pure anymore. Because then you have a database call. But in the moment when I read this code, when I look at this code, it is clean. I know what it does. I can reason about the code, so I can understand what the code does. The types are restricted. And I can easily test it. That's the next nice thing. I don't have to handle the futures. I don't have to write some mocks or whatsoever. It's just a function. I put something in, I get something out. The last step is to apply it. So how does it look like in our server? We say, we call this records for user. We say it has to be a future. Right now, I'm not sure if you have to write it because this information is provided on by the DB reader, but doesn't matter here. I supply some user ID. I get back the future, the function, or this Kleisli, and now I just have to also apply the signature or the parameter for the Kleisli. In this case, it's implementation of the user reader interface. For our production system, that would be a database access. For our unit tests, we would say our context is ID, which is just a nice trick to pretend we have some higher kind there. In the end, we just work on the type A, so the higher kind just is removed. And we add some fake reader. It can have static data or whatsoever. So this call down there is completely pure and easy to test. You have no futures, no side effects, nothing at all. As I said, this is one way to solve it. But with the tools we got in this talk, I would say it's a nice way to solve it. You can also, this is comparable with the way when you use free and all the other stuff we might talk or have a talk at another time about. When you have side effects, you try to push them to the outer bounds of your application. You try to push them to the caller of your function. So you have to try to encode them in your return type. This is more or less my presentation. I just have some follow-ups. As I already said, or during this question, I talked about cats. That's usually the library I use when I use monads and all free monads and all the stuff, because I think it has a nice implementation. It's a good read. Actually, the code is really good written. It's good. What do you got there? When you go to the GitHub project, you have the kernel package. It provides you all these algebraic structures or type classes which represent algebraic structures. That includes the order you have already seen. That includes monads, semi-groups, groups, and all the stuff for math. You have the core package. This includes some more type classes. Also, everything which is related to category theory, which means functors, monads, applicatives, free monads, No, free is something else. This is another package, but all the stuff you get from there. And of course, you get on this package, you also have some implementations, usually for future either option. Usually this is free. And you have the laws package. It's a collection of classes providing tests for your type classes. So when you write your own implementation of a monad, you can use the test class for monads from laws, put it into a Scala check test, and you cannot prove it, but you can be really sure that your implementation follows the properties or laws of a monad, or not if the test fails. So the law package is about testing your implementations of the type classes. Yeah, then this is my last slide. This is my talk. If any question is left, ask it now or approach me later. Yeah, I'm done.